Good afternoon everyone, I'm Viren, and with me is my teammate Yiheng. Our presentation will be about our Kaggle project, Zillow's home value prediction. We will first go over the introduction, followed by industrial approach, feature engineering, and example learning. Let's start off with the introduction, which includes the problem statement, data description, and exploratory data analysis. The objective of this competition is to predict the log error between their Z estimate and the actual sales price, based on all of the features of a home. The log error is defined as the log Z estimate minus the log sale price. Accuracies of the Z estimate models are evaluated using the mean absolute error (MAE) between the predicted log error and the actual log error. We first explore the dataset and look for trends that are evident in the dataset. This helps us better understand the problem we are trying to solve and find clues on where to improve. There are a total of 4 files that we will be conducting data analysis on. The train 2016 and train 2017 contains the parcel ID, log error, and transaction date. The properties 2016 and properties 2017 file have all the properties with their homes features from 2016 and 2017 respectively. I'll move on to explore individual features and variables. The log error field is the target variable for the competition. Therefore, we ran some analysis on it. The log error is normally distributed with a few outliers at either end of the positive or negative values. During data pre-processing, these outliers will be taken into account and removed if needed. There's no clear trend in the number of transactions each month in both 2016 and 2017. However, there's a slight drop in the number of transactions in the later part of the 2016. From October 2016 onwards, the number of transactions reduces by quite a bit. In addition, most parcel ID only appears once in the dataset, meaning a single house is only transacted once in both 2016 and 2017. The properties files and training data will be combined so further data analysis can be done. After combining, there are many missing values that are represented by as NaN. These values will either be removed or edited before modeling. Since we are just exploring data, these values will not be removed yet. The NaN values will be replaced with the mean, and the correlation coefficient will be calculated. The correlation of the target variables with the given set of variables is low overall. It ranges from negative 0.02 to 0.05. Therefore, there's no trend or pattern that can be identified from the correlation coefficient. And there are some variables without any correlation values since they only have one unique value. We'll be taking these variables with higher correlation values and do some further analysis on them. For 2016 and 2017, there are some slight differences in the variables that have a high correlation value as compared to others. Therefore, we will be exploring the years separately from this point onwards. The important variables identified in the 2016 training set are highly correlated with each other, at values nearing 1, which is the highest correlation. Further analysis will be conducted on the individual variables. The range of log error narrows down with the increase in finished square feet trough variables. This means that the large houses are easiest to predict as compared to smaller houses. The calculated finished square feet have an extremely similar distribution as compared to the finished square feet trough. This explains why the correlation between these two variables is so high. Generally, the median log error remains the same as the number of bathroom counts increases. However, as the number of bathroom counts increases, the range of log errors also increases. As seen from the chart, the block spot becomes bigger. Similar to the bathroom count, the number of bedrooms does not cause the median of log errors to deviate much from one another. The log error is distributed the same across all bedrooms. By combining both the bedroom counts and bathroom counts, we created a 3D representation of the bathroom and bedroom count versus the log error. Even after doing so, there isn't any trend that can be picked up. Similar to both square feet trough variables, the log error decreases as the tax amount increases. The larger the house, the more tax is to be paid. Therefore, the graphs are similar. As for the year built, there is no clear trend between the log error and the year the building is being built. The log error is equally distributed between the years. Moving on to the analysis of year 2017, when compared to 2016, the important variables are not as highly correlated. However, there are still some variables that are very highly correlated. Further analysis will be conducted. Similar to the year 2016, the range of log error narrows down with the increase in finished square feet trough variables. The calculated finished square feet for the year 2017 also have an extremely similar distribution as compared to the finished square feet trough. This explains why the correlation between the two variables is also high. Generally, the median log error remains the same as the number of bathroom count increases. However, the number of bathroom counts increases, the range of log errors also increases. As seen from the chart, the box plot becomes bigger. This behavior is the same as in year 2016. Similar to the bathroom count, the number of bedrooms does not cause the median of log errors to deviate much from one another. The log error is distributed the same across all bedrooms. Similarly, even when combining both bathroom and bedroom count into a 3-dimensional plot with log error, there isn't any trend that can be picked up. The garage square feet have a similar distribution as the square feet variables. As its value increases, the log error decreases as well. This is because a larger garage will mean a larger house, which means the square feet increases as well. Therefore, the distribution is similar. Similar to the year 2016, there's no clear trend between the year the building is being built and the log error. I will now pass on my time to Yiheng to talk more about initial approach to modeling.
Now I will talk about the team's initial approach. After exploring the data, we will prepare the dataset before it can be fitted into the models. So from the exploration of the dataset, we can observe that there are some outliers in the log error. So we'll be removing those outliers in the training dataset. There are also many empty entries represented by NaN, and those columns with more than 98% empty entries will also be removed. Unnecessary variables like unique IDs, description, and codes will be removed as they do not add value to the training data. And lastly, transaction dates will also be converted to a new format for easier processing by the model. So this is an outline of our data pipeline. Firstly, the Kaggle datasets are cleaned into a train DF and test DF. The models we created are evaluated based on the test DF, and the CSV file that we obtain is then sent to Kaggle for submission. The train DF file is further split using an 80-20 split into a training dataset and a validation dataset, and we'll be training on the 113 features left. We will determine the effectiveness of our models based on two metrics, the root mean square error, RMSE, as well as the mean absolute error, MAE. So based on Kaggle submission guidelines, all submissions are evaluated on MAE based between the predicted log error and the actual log error. Hence, we decided to follow accordingly when evaluating our model's performance, and we aim to have a low MAE and a low RMSE. For our models, we will be using the boosting models. So boosting algorithms is a method of converting weak learners into strong learners. A weak learner represents a learning algorithm that only predicts slightly better than randomly. Boosting algorithms are able to handle mixed data types where categorical variables do not have to be one-hot encoded. So this is especially useful for us as our training dataset has a good mix of continuous and categorical data. Multicollinearity of features also does not affect the accuracy and prediction performance of the model. Since most of our features have high correlations with one another, using boosting models is beneficial as we do not need to remove these features or re-engineer them to decrease their correlations. They are also robust against overfitting and outliers, so using many weak learners that underfit and combine those predictions into a strong learner, they reduce the overfitting variance of the model. So boosting algorithms helps to handle noisy data with little impact on model performance. Our evaluations will be based on these three models, AdaBoost, XGBoost, and light gradient boosting model. Adaptive boosting sequentially grows decision trees as weak learners and punishes the incorrectly predicted samples by assigning a larger weight to them after each round of prediction. The algorithm learns from previous mistakes. The final prediction is the weighted median for regression problems. We experimented with different N estimators and learning rate to arrive at our best model for AdaBoost. RMSE and MAE are calculated based on the validation dataset. We noticed that increasing the number of N estimators has little impact on the RMSE and MAE, whereas lowering the learning rate results in a lower RMSE. We built our final model based on our learning rate of 0.3 and N estimators of 100 and submitted it on Kaggle for evaluation, and the results we got was an average performing score on the public and private leaderboard. Extreme gradient boosting is a scalable, distributed, and gradient boosting decision tree machine learning library. It provides parallel tree boosting and is the leading machine learning library for regression, classification, and ranking problems. It has great execution speed and provides excellent performance for regression predictive modeling problems. And what we have noticed is that XGBoost has been dominating in applied machine learning and also in Kaggle competitions for structured or tabular data. So we decided to incorporate this model in our experiments. We will use the default sampling method, which is uniform, and this is where the training instances has an equal probability of being selected. And after various tweaking with the parameters, we arrive at these parameters for the best model in terms of lowest RMSE and MAE, as we can see here. So our model is then submitted to Kaggle for evaluation, and we arrive at a slightly better performing model than the AdaBoost. So light gradient boosting model is a fast, distributed, and high-performance gradient boosting framework, and it's also based on the decision tree algorithm. And its main difference from XGBoost is the tree growth. So for XGBoost, it follows a level-wise tree growth, whereas for light gradient boosting model, it follows a leaf-wise tree growth. And the main reasons we use light gradient boosting model is as follows. It's because it enables a faster training speed and higher efficiency. So this is especially helpful in our training because XGBoost tends to take a lot of time during the parameter tuning. And it also uses a lower memory usage, so because it actually replaces the continuous values to discrete bins. And this is very helpful as well because we have many issues with RAM usage on Google Colab. And lastly, light gradient boosting model is compatible with very large data sets and is capable of performing equally good with large data sets as well as it reduces the training time a lot as compared to XGBoost. So after our experiments, we realized that the light gradient boosting model actually gives us the best results, but we were still quite we were still ranked quite low on the leaderboard. So as such, we think that more can be done to improve our models, and the team decided to dive into the features and use the findings we discovered in the previous EDA part.
We have decided to create a few new features to be added into the model. The life of property is calculated by subtracting the year the building was built with the year 2018. The life of property is the number of years the building has been built. It provides more insight as compared to just knowing when the building was built. We are able to immediately identify the old and new buildings. The proportion of living area is the second feature created. It is calculated by taking the ratio of calculated finished square feet over the lot sizes square feet. The proportion of living area is the ratio of living area to the total size of the land. The ratio of built structure value to the land area is the third feature created. It is calculated by taking the ratio of structure tax value dollar and land tax value dollar. The ratio is the ratio of structure tax over the land tax. The fourth feature we have created is the location. The feature is being created by combining the latitude and longitude. Since both the features represent the position on Earth and they come in pair, it makes sense to combine both of them into a single feature. The fifth feature we created is the value ratio. It is calculated by taking the ratio of tax value dollar over tax amount. The feature is the ratio of tax property over the parcel. It gives insight into how much of the total tax is made out of property tax. The sixth feature we have created is quite similar to the previous feature. The total tax score is the product of both tax value dollar and tax amount. The seventh feature, zip count, calculates the total number of properties in the zip. It is calculated by finding the number of cities and mapping it to the regions to create a feature that counts the total number of properties in the zip. The last feature calculates the amount of extra space available. It is calculated by getting the difference between the lot size square feet and calculated finished square feet. We used XGBoost to determine the importance of our features and found that the features we have created made it into top 20 important features. This shows that the features we engineered could be useful. The results after using new features are as follows. We realized that with the newly added features, the private score and public score for light GBM resulted in small improvements, but it worsened the performance for AdaBoost and XGBoost model. We felt that our new features are important. They were part of the top 20 important features. We decided to stick with our new features and try a different method to improve our model performance. Yiheng will now move on to explain the next approach we took and lastly close off the presentation.
Now, I will talk about our final approach, ensemble learning. So the main objective of ensemble learning is to improve model performance in terms of accuracy by aggregating the predictions of multiple models. This is done by constructing a set of base models from the training data and making predictions by combining the predicted results made by each base model. So for our experiments, we'll be using the three base models we created before, AdaBoost, XGBoost, and Light GPM. And we will use the same parameters as before. We created an ensemble class and the stacker used was linear regression. And we implemented stacking by doing multiple predictions on the test dataset and aggregating them. The entire train dataset was included in this training, and we did not split the train dataset into train and validation. Overall, we managed to only run it on 2 splits due to the Google Colab RAM limitations, but we were actually able to achieve better results. As you can see here, the ensemble method produced the best results as compared to our previous models. It allowed us to achieve also a better ranking on the private and public leaderboard. So we managed to achieve top 9.2% on the private and 11.6% on the public. So in conclusion, exploratory data analysis was especially useful at the start because it helped us understand the dataset and also define the way we approach this prediction problem. It allowed us to identify similar classes and provided a stepping stone for data preprocessing as well as feature engineering. However, we faced some limitations in the model building part because of our limited computational abilities. The total dataset had a size of about 1.3 gig, and this actually took a lot of time to train because we were using Google Colab. And this was especially hard during the parameter tuning. As such, the parameters that we used were actually determined by test and trial methods and may not have yielded the best results. We could have planned ahead of schedule and understand how long each training will take, and this could have actually allowed us to have enough time to fully test and evaluate our models. And lastly, we realized the ensemble learning method by combining AdaBoost and XGBoost and Light GPM achieved one of the best results that we've gotten. And further work could be done on this part. So what we could have done is actually explore category boost, which was shown to have one of the best performances for this Kaggle competition. So maybe by incorporating category boost with the ensemble learning, we could have achieved a better result. Overall, this project has largely improved our knowledge on machine learning, and it was especially an enriching experience being able to participate in a Kaggle competition. Thank you.